Okay, so the next speaker is Zhengyi Zhou from AMSS China, and he will talk about feelings of contact links of isolated quotient singularities.
Thank you. I would like to thank the organizers, especially Leonardo, for inviting me here. And this is my first time in Rio. And my talk here is more on the topology side, not anything about dynamics or groups. But I will be using these tools has appeared in the previous talks, for example, in Miguel's talk yesterday. And I hope I can come back later with applications in dynamics. But today, let's focus on topology. OK, so let's first talk about the basic subject, which is the links of singularity. So if you have a singularity at 0, then you can define a link, which is just a boundary of a small neighborhood. And this is a contact manifold. And the contact structure is given by the maximum subspace, which is a complex subspace. Okay? And this contact manifold carries a lot of information about the singularity. And we have basic examples. The first example is a standard contact sphere. And this is actually the link of a smooth point. Okay? And the contact structure, now I'm not using contact form, I'm using this complex tangency language. And the second example is this quotient. So we can consider the quotient on a sphere, which is just by multiply -1 to every coordinate. This will preserve the contact structure. So we get the contact structure on the real projective space. But this is actually the link of the Z2 quotient singularity, which is just this Cn quotient by Z2, which is the orbifold. And more generally, we can consider a finite group G, which is inside the unitary group, and such that the Cn quotient by G has an isolated singularity. And the link is just a spheric quotient by G. And there is another family of singularity, which is kind of an important family, which is called the Bursztyn manifold. And this is just the intersection of this equation, algebraic equation, intersect with a sphere. And the singularity is corresponding to this equation. And this is defined a singular variety, which is the singularity is at 0. OK, this is all these are contact manifold. And another thing in my title is filling. So I know you must know the definition, but just write down the definition. So the filling. I will be interested in strong fillings and exact fillings. So strong filling is just a symplectic manifold such that the boundary is Y, and there's one form lambda defined near the boundary such that the Liouville vector field X is pointing out. So this is some convexity condition. And last one is we have compatibility, which is the kernel of this one form is the contact structure. So this is a one form. This lambda is a contact form restricted to the boundary. And this is called the exact filling if the one form is defined everywhere. So let's go back to our situation of singularity. So in singularity, we have a particular nice construction of strong fillings and exact fillings. So first of all, any resolution, which is a strong, will give you a strong filling of the link of the singularity. So, but by the celebrated theorem of Hironaka, we always have resolution over Z. So I'm talking over Z. So everything is actually complex manifold. OK, so we always have strong filling. And what about exact filling? So there's another way to get a smooth manifold out of a singular variety, which is called smoothing. And smoothing is just basically you trying to consider a family of these varieties. With the central fiber is this singular one, and the nearby one could be smooth. And if you have this thing, then you will get a Weinstein filling or exact filling. But unfortunately, smoothing may not always exist. In fact, in our situation, there's a classical theorem. I didn't put on slides, but there's a classical theorem. Lens Singer in 71 that Cn quotient by G has no smoothing if the dimension is at least 3. So when dimension high, there's no smoothing. Of course, this is not showing the contact link has strong filling but not exact filling, because not all exact filling coming from smoothing. In fact, this is already known in dimension 4. There are examples. And of course, there's one basic example is the quotient singularity, the simplest quotient singularity is C2 quotient by Z over 2. The link is the RP3, which already appeared in several talks. I think it will also appear in talks tomorrow. And this thing has smoothing, which will give us the exact filling, which is a cotangent bundle of sphere. It also gives us a resolution, which is a total space of degree -2 bundle over CP1. These two spaces are same space, but the symplectic form are different. So here, the S2 will be a Lagrangian, but here the CP1, also the S2, will be a symplectic submanifold. So these are like topological same, but symplectically different. Okay, so why do we care about fillings? To me, the reason we care about filling is first this fundamental theorem observed by Gromov and Alashberg in the late 80s, which is not every contact manifold arises as a boundary of a symplectic manifold. In particular, they show that over-twisted manifolds have no symplectic filling. Okay, so you can view this as having filling is a geometric criterion for tightness, and tight contact manifold is kind of the more mysterious contact manifold in contact topology because over-twist contact manifolds are more or less governed by H principle. It in some sense can be understood, like you have structure for them. So we can actually using these different types of filling to refine the tightness. So just putting different flavors of filling here. So we introduced two filling, which is exact filling and strong filling. We also have something called Weinstein filling and weakly filling. So by definition, these are our inclusions of contact manifolds. And the most general one is tight because of the theorem above. A priori, these are just inclusions. But by now, we already know that these inclusions are all proper in every dimension greater or equal to 3. But in this talk, I will focus on the middle one, which is exactly fillable contained in strongly fillable. That is, I want to understand which contact manifold has strong filling but no exact filling. So in this line of direction, the first result is due to Gugini, maybe around 20 years ago. That is, there is a strongly fillable but not exactly fillable contact threefold. And recently, there's a generalization of Min, like he constructed many more such manifold in dimension 3. And in higher dimensions, there's a guiding question by Alashberg, which says that the real projective space is not exactly fillable only if n is greater or equal to 3. And we know that when n is 2, this is RP3. It's exactly fillable by cotangent bundle of sphere. And why this conjecture is expected is because, first, it's very easy to show that these things has no Weinstein filling when n is greater or equal to 3. This is actually an easy exercise for a first-year graduate student, I think. Yeah. Anyway, so this is a conjecture. And the good thing is this contact manifold seems to be really kind of simple. Okay. So in 2020, I proved the conjecture for most cases, which is just when n is not power of 2. And also there exists strongly fillable but not exact fillable in any odd dimension higher than 3. And first, I want to mention that I want to say what is the importance of n bigger or equal to 3 condition in Alashberg's conjecture. Of course, we know it doesn't hold if n is 2. To me, from the proof, I think the reason this condition is there is because this is a threshold for singularity to be terminal. I will explain what is terminal singularity in a minute. Roughly speaking, it's kind of a simple singularity. It's something you have to consider in the minimal Borel program in higher dimensions. Yeah, and here I have a condition that n is not a power of 2 because this is a quotient by Z2, so power 2 is the harder part, and I didn't know how to solve it back then. Yeah, okay. And but from this perspective of terminality, I made a conjecture that this thing is not exactly fillable if this singularity is terminal. So it's a more general conjecture. And this talk will be about some updates on this conjecture and also Alashberg's question. Okay, so the first main result I want to talk about is his conjecture holds. So I fill in the gaps, which is every RP2n minus 1 is not exactly fillable whenever n is greater or equal to 3. So the power of 2 part is solved. And I also want to bring in another perspective, which is there's actually a more well-known theorem which actually fits into this picture, which is this theorem of L-Ashberg, Fleur, McDuff, which shows that this sphere, a symplectic filling of sphere, is actually diffeomorphic to a ball whenever n is greater or equal to 2. Okay, and in fact, you should view this sphere as a link of a smooth point. And the smooth point is a terminal singularity if and only if n is greater or equal to 2. So from this, I can make the following conjecture that Cn quotient by G is terminal. If this is true, then any orbifold filling of this contact link have unique diffeomorphism type. Okay, so of course, this conjecture is still stronger than L-Ashberg, Fleur-Magdorf. You have to show that any orbifold filling has no singularity. Okay, and I sort of know this conjecture is true for G is mod 2 and n is odd. And also, the conjecture is true for G is identity, that is for sphere, but you have to show that any orbifold filling has no singularities. This is joint work with Fabio Gironella. So we know this conjecture is true for a few cases. Yeah. And okay. But you see that this conjecture will imply the previous conjecture, because if you know that orbifold filling have unique diffeomorphism type, you do not have manifold filling because this is a unique type. You have to have a singularity. So this is actually stronger than the previous conjecture. But I don't know how to approach this conjecture directly. I always need to first prove there's no exact manifold filling, and then try to argue that what type of singularity can't have, and then to deduce this uniqueness result. Okay, so this is the main result. Okay, so let me talk about these terminologies pop up in the definition. So first, let's talk about what is a terminal singularity. I'm not an algebra geometrist, so I will tell you about the definition of terminal singularity from a topological perspective. So given a singularity, we assume that the first chain class of the contact structure is 0 rationally. And then we can consider resolution pi such that the exceptional divisor, the pi inverse 0, has normal crossing divisors EI. That's the most nice case. You can always achieve this. And because of the first chain class of the contact boundary 0, you can view the first chain class of the resolution as a class in the relative cohomology group. And this, through the Lefschetz duality, can be written as a linear combination of this AI dual of EI. And we can define the so-called minimum description number, MD, is the minimum number of AI among all resolutions. Okay, and the singularity is called terminal if this minimum description number is positive. That's the definition. Okay, and an interesting part is this terminal condition actually has a contact geometry interpolation. So the interpolation looks like this. We start with a contact form alpha and a reorbit gamma, and we can define the lowest SFT degree. And the first part, Collins-Cinder index plus n minus 3, is the Euro SFT degree. But this gamma is not assumed to be non-degenerate. So you can have this kernel here. This can have a dimension. So roughly speaking, if you come in a more spot family, this is the lowest degree you can get after a generic perturbation. Okay? And my Collins-Cinder index here is a rational one because I'm assuming the first chain class is rationally 0. You can define a rational Collins-Cinder index. This already appeared yesterday in Miguel's talk. And we can define so-called highest minimum index, HMI. This is defined to be the infimum of all the lowest SFT degree of a contact form, and then take the supremum of them for all the contact form. So roughly speaking, this is taking the lowest degree of the essential reorbit. So typically, you see this is something it's really hard to compute. But in many examples, this reorbit always will be something non-trivial in certain type of Fleur theory or SFT. Yeah. And OK, so we have this number. It's very hard to compute, but it's defined. So a beautiful theorem of MacLean. Yes? Yeah. And the beautiful theorem of Maclean is this thing, HMI, which is a contact invariant, is actually the algebraic invariant. He shows that if your singularity has these properties, this numerically Q Bursztyn is a fancy way of saying the first Chern class of contact form vanishes rationally. And you also need to assume that this H1 is 0. This has to do with the weird definiteness of Collins-Cinder index, because this H1 is sort of a space how you can reparameterize your S1 bundle. Okay, and he shows that the HMI is twice of the minimum description number whenever it's positive, non-negative. And if one of them is negative, the other is also negative. So in particular, the terminal condition is a contact property. But I also want to mention that from this, we see that this terminal condition is actually some index positive condition. This HMI is positive. Although for our talk here, we don't actually need to use this theorem. It's just to show that this contact property is, this algebraic property is actually contact property. For quotient singularity, this theorem is already known like in 80s, and we can actually work out by hand. Okay, so another tool I want to use is Symplectic Cohomology. This already appeared in several talks, and I will be using cohomological conventions. It's the same thing as all the Symplectic homology appeared in the previous talk. And the thing is, this thing has its own reason to be called cohomology and homology at the same time. But despite the different definition, it's the same invariant. It's always the same invariant. Okay, so this is just roughly speaking, it's a Hamiltonian fluid cohomology of completion W hat. Here, let's assume that W is exact. So let's first assume W is exact. Okay, so like the generators, there are two types of generators, which is first points on W. You take a Hamiltonian which is 0 on the filling part and grows quadratically on the cylindrical part. And the generators are points on W and non-constant orbits on the boundary, Reeb orbits. And then they will form so constant point will form a subcomplex, which will compute the cohomology of the filling. And the Reeb orbits will form a quotient complex where compute the so-called positive Symplectic cohomology. And they fit into this tautological Lagrangian sequence. And there are some nice properties of this Lagrangian sequence is, first of all, the first map, this map, is a unitary ring map. Okay? And from this, we have a very easy application, which is if this SH plus map to the H cohomology, this connecting map to the cohomology of filling, and then restrict to the 0 part. If this map is non-zero, then the Symplectic homology is 0. Because if this is true, that means 1 plus something is killed in the Symplectic homology, but 1 plus something is a unit, so it kills everyone. This is consequence that the first map is a ring map. And from this vanity result and the Lagrangian sequence, we know that the positive Symplectic homology is the same thing as the cohomology of the filling. And so you can kind of transfer the Reeb dynamics into the topology of the filling. And the last one is about grading. It's always C2 graded, but it can have C grading or Q grading if you have some extra topological information, the vanishing of Chern classes. Okay? And this is very basic about Symplectic homology. Another piece I want to use is secondary coproduct. Okay, so we know that we have product, which is so-called pair of fans product, counting things like this. And you can do the similar thing, counting the coproduct, but maybe this should be called a pair of pans coproduct. But I want to count things on SH plus. But observation due to Seidel says that this thing is very degenerate. The reason is we basically count things, when we count things, we pick Hamiltonian, fix a Hamiltonian H with slope A. So we can solve the equations so that here the Hamiltonian is slope is, AH. Here we have BH. Here we have CH. So we can like multiply some weight to it. So the Floer equation solves not H but AH. We have to worry about maximum principle to get things well defined. So for the maximum principle to hold, we basically need to require that B plus C is greater or equal to K to imply maximum principal. Okay. So from this we can see that the SH plus the coproduct on SH plus will vanish because we can first consider sort of the weight A is 1, B is 1, C is 1. But this defines our coproduct. But we can start pinching here to B to 0. And in this family, we still have this relation that B plus C is greater than A. So the maximum principal still holds. We get basically homotopy. But when this collapses to 0, it's no longer evaluated in SH plus. So this shows that coproduct, the naive coproduct, is 0 on homology. But the suggestion by Seidel and later carried out by Akon and Wangshar and much more general form is they define this secondary coproduct, which is because we kind of have two types of degeneration. We can pinch the left leg or we can pinch the right leg. So we can consider a family like connecting them. And you have two vanishing, so something in between can be like homological visible. So this is like how you define a messy product. Okay, so this is the secondary coproduct. Positive Symplectic cohomology is on here. And the significance of this secondary coproduct is the following, due to Eliashberg, Natra, and Lazarev, where they show that the secondary coproduct, when you compose with the connecting map from SH plus to the cohomology, it will give us the commuted diagram like this. Okay? And so we have to explain what is this guy. This capital delta. This is the coproduct on the cohomology, which is a dual of the product on the dual of this space, which is a compactly supported cohomology. So it's a dual of the coproduct on the compactly supported cohomology. And it actually captures the intersection information of the filling. So this is not purely topological. It's actually, because the intersection form is something related to the manifold structure. Okay, so this is a key thing. Okay, so let's go back to our situation at hand. We want to understand fillings of this quotient singularity, the link of quotient singularity. And what we know is it has a natural filling, which is given, the Cn quotient by G. And this is orbifold. So this make a demand to define symplectic cohomology for orbifold. So this is already appeared yesterday in Miguel's talk. So I will talk briefly about how you define such thing. So first of all, when you think about defining Floer theory or Gromov-Witten theory, first thing is you have to set up the Fredholm setup. You have to write your moduli space as a zero set of some Banach manifold of a Fredholm section, right? And then compactness, transversality, all these things. So first thing is we have to figure out what's the ambiance space to accommodate the moduli space. So what's the space between orbifolds? So the thing is WKP maps between orbifolds is actually, again, an orbifold, but it's a Banach orbifold. You have to assume KP is big enough so that it's continuous. And why is this true? So first of all, we can represent orbifold by a so-called état proper Lie groupoid. It's just a fancy way of saying orbifold atlas. Okay, so groupoid is a category where each morphism is invertible. So you can kind of, this is how you can view a manifold. For example, if you have S1, and you can get a groupoid out of it, it's just you take this, here you have a chart, here you have another chart. So the object is just these two charts. And the morphism is identity and the identification of these two p's. So for every manifold, you can, and an atlas, you can cook up a category out of it. That's kind of just chart. So now we have, of course, different groupoid can give the same orbifold, so we have to talk about equivalence. That's called the Morita equivalence. And so since we represent our orbifold by groupoid or categories, the maps between categories are functors. Okay, so we have functors between groupoids. But for functors between categories, we have self-symmetry, which is natural equivalence. And in the case of groupoid, every natural transformation is natural equivalence. But here you can actually see that proves that the functors between groupoid, this thing, form a Banach manifold. And this, when quotient is this equivalence, you basically get this maps between groupoid is modeled on Banach manifolds. So that's kind of justify the first sentence that it's a Banach orbifold. And you have to refine Lie groupoid to get all the orbifolds. So this is all abstract. Maybe it's easier to talk about a concrete example. And this example shows, I guess, all the key features. That is, we consider the orbifold maps from S1 to point quotient by G. So this is the orbifold. So when you write it as a groupoid, its object is just a point, and the morphism is this group G acting on itself. Okay, so we can first view this S1 as a kind of stupid atlas, which is covered by S1 itself. The objects are S1, morphisms are always identity. And then there is only one functor to this category, which is sending object to point and send every identity to identity. So there's only one functor, but there's a G family of natural equivalences, which is sending the element to element in G, because natural equivalence send element to a morphism. Okay, so we get basically a functor with a lot of symmetry. And, but we can also view this S1 as another category, another groupoid. This is not quite atlas, but it's also fitting to the definition of proper Lie groupoid. Roughly, if you have to enlarge it a little bit, but it's easier to write in the closed interval. So this is some object is the interval, the morphism is identity, and there's one more gluing 0 and 1. This will give us the circle again. But if we use this category to consider what are the functors to point quotient by G, we basically need to record where 0 to 1 is mapped to. So the functors will be parameterized by G. Okay? And the natural equivalence, again, is parameterized by G, but it's act on functors by the conjugation. So the first thing is actually only capture one orbifold map, which is just the kind of identity here. And in fact, the second point of view capture all the orbifold maps. Okay, so this is something. Okay, so this justifies the last step. You sort of have to refine your Lie groupoid to get all the orbifold maps. Okay, and there are other things we can learn from this example. Is first of all, the singularities of the space of maps. So the space of maps of orbifold is orbifold. So you can talk about the singular maps. The singularity is completely inherited from the target orbifold. It has nothing to do with your domain orbifold, like previous, the automorphism coming from the group G. Okay? And the second one is constant maps between orbifolds are not the target orbifold. Because in the case of manifold, we know the constant maps from a manifold to a manifold is just the target manifold, right? But this is no longer true for orbifold, because the previous example, we consider constant maps from S1 to this, and we see that actually the maps is sort of G quotient by the conjugation group of G, which has like a lot of point and symmetry. Okay. And so we can talk about constant maps from S1 to the orbifold X, which is in the special case was considered previously. This is called the inertial orbifold, lambda X. And the cohomology of it is called chain-run cohomology. So inertial orbifold is actually just a space of constant loops of orbifold. And chain-run cohomology is the cohomology of that one. So now the cohomology is just view this thing as like take the orbit space of this orbifold and take the usual cohomology, singular cohomology of it over Q. Okay. And another thing is when we're trying to think about a Floer series or holomorphic curves, if you think about removal singularity, if you have a curve with puncture with finite energy, it will converge like you have an extension. But what you actually prove is it converges to a constant loop. The length goes to 0. So in the orbifold case, we don't have a removal singularity. The singularity can land in the initial orbifold. So really, you should consider, like in the bubbling, your connecting point is a puncture, and it evaluates in the inertial orbifold. And from all this, you can think of like defining Gromov-Witten theory and Floer theory of symplectic orbifold as counting finite energy curves from puncture smooth surfaces. So you don't have to, because the initial definition of Chen and Ruan, they consider kind of orbifold maps from orbifold surface to orbifold. And when I'm trying to understand their work, it's a bit too hard to follow because you have so many orbifolds. And in fact, you don't need to worry about the domain. You can always take throughout the singularity. It's a puncture surface. And the removal singularity will fill in it automatically. If you want, you can make it a map from orbifold to orbifold. OK. So roughly, this will tell you what's a Fredholm setup. OK. So let's go back to the actual case we define the symplectic homology, which is when W is orbifold with a smooth contact boundary. Exact orbifold with some contact boundary. And this actually has very strong restrictions on this orbifold because if the singularity is not isolated, then the singularity itself can form a symplectic suborbifold. If it's exact, this thing has to touch the boundary. But the boundary is manifold, it has no singularity. So the only possibility for the singularity is isolated singularity. So when I say it's an orbifold with smooth boundary, contact boundary, I'm kind of assuming that we only have a bunch of isolated quotient singularities and then a smooth coordinate. So it's really restrictive one. But this setup has a lot of benefits in the analytic setup that allows us to define the symplectic homology group without using any fancy thing. We define this group using nice choice of almost complex structure. Okay, this is joint work with Gironilla. Okay, and so what's the problem here? So it seems like everything is like just manifold. So there's one thing. It's again for transversality issues. So as we know, since it's exact, we do not have any non-constant finite energy puncture spheres into the orbifold. But you can have constant spheres with punctures into the orbifold. But in this case, you can have something which is not cut out transversely. This is a problem of transversality, even in this exact orbifold case. So here is an example. Let's consider a 3-element G1, G2, G3, such that the product is identity. And we can consider a constant map from like a sphere with 3 punctures. So it's like this is a sort of a configuration of a surface. And we can consider a map to a quotient, Cn quotient by G, with the asymptotics are G1, G2, G3. So this is considered as inside the inertial orbifold, but it's determined the conjugacy class of G1. So this map is actually, you can cut this open to give it an orbifold chart. And this morphism is sent to G1, this is sent to G2, and the other one outside is automatically G1 times G2 inverse. Okay, and this is a constant map, it's holomorphic. And the Fredholm index is given by this number, 2 minus 2hg1 minus 2hg2 minus 2hg3. And this age invariant is just, you can first diagonalize this G, and you have these eigenvalues. And AI is some integer between 0 and it's smaller than the order of G. And you sum them up. This is a rational number. That's the age invariant. We can show that this age, G1, G2, is always smaller or equal to age G1 plus age G2. This is actually a fun linear algebra exercise. It took me some time to figure out how to prove this. But anyway, this is always true. That's we imply this thing is always non-positive. But in fact, if you choose your G wisely, you can get this index to be negative. But this curve can never be perturbed away because it's always holomorphic. Okay, so this is the problem of transversality if you only perturb J. But good news is we don't have to worry about these things if we are only interested in defining the group. if you have only 2 punctures, this thing, non-transverse constant holomorphic curve does not appear. So that's why we only define group. And if you want to define ring, this will appear, and that's the reason why we didn't define it. But of course, if you apply other virtual techniques, you can get the ring structure. Okay. So what are the properties of this symplectic homology of the orbifold? First is this, again, we have this long exact sequence. So now we have to replace the constant, so the constant loops of the filling now is changed to change it to the chain-run cohomology. That is the reason why we have this long exact sequence. And again, another feature is this thing is defined over Z. This is some special feature when we consider its orbifold, exact orbifold with manifold boundaries, so only isolate singularities in the interior. And the Z theory actually requires a special setup. We need to consider Hamiltonians, which is 0 on the W and linear on the cylindrical end. So it's more like an SFT perspective. But we know that in symplectic homology or symplectic cohomology, we can allow any Hamiltonian to define the symplectic homology. As long as it's linear outside the compact set, you can do whatever thing in the interior. You will get the same invariant. This is no longer true for this orbifold theory. So the problem is hidden in the homotopy argument. And you can actually see this can never be true because of the next theorem, which is the basic computation for this CN quotient by G. Since it's defined over Z, it can be defined over any ring. And we show that with Fabio, we show that this symplectic homology is 0 only if G is invertible in this quotient. Okay. So in particular, Z coefficient of this symplectic homology is never 0. It's always a lot of torsion. But if you try to use a random Hamiltonian, like a general Hamiltonian defined, you can always use Hamiltonian like AR square. For A is very, very big. And this can guarantee that the Hamiltonian orbit will have very large Collin cylinder index and no other orbit except the singularity. So if you allow these type of Hamiltonians, you can show that this symplectic homology is always 0. Okay. And so you see that the theory, if you want to define over any Hamiltonians, then the theory is not well defined over Z, because the homotopy of continuation maps has a problem. Basically, you have some constant curves you cannot perturb away. It's always not cut out transversely. Okay, and the next thing is Ashberg, Natural, Lazarev. Their theorem holds for CN quotient by G. As I said, the problem of generalizing this structure is constant spheres. Of course, when we consider this pair of pens, we can have a problem like in the example. Okay? But in the case of CN quotient by G, this is a very special example. You have a lot of topological informations. You can actually show that this thing does not appear. So I don't know whether Ashberg, Ganatra, Lazarev result for general exact orbifold. I mean, without using fancy techniques. Okay. Anyway, so this is true. Just you can prove by hand. So what is this delta here? This delta is kind of the coproduct on the chain-run cohomology. It's called chain-run coproduct, or it can be viewed as a dual of the chain-run product of the compactly supported cohomology. And I just want to mention one thing. So this is counting kind of holomorphic curves with 3 punctures of but it's always constant. But this has a property which we will be using is this. G is conjugate is a class. It's G tensor G inverse. So it's actually non-trivial on the identity class. This is somehow like the unit in chain-run cohomology. Okay. This is sort of saying that you have non-trivial intersection form. CG is the size of commuted group commute with G. Okay. So to talk about this, so let's go back to this quotient singularity, and we have this thing is very nice. You can work out the Rib dynamics very nicely, and In fact, you can consider this space, VGL, which is sort of, because the ripple flow here is just this e to the ti that multiplies a complex number here. So this space is like describing, like after time L, you can close up with a group element G. So this will be a ripple orbit on the quotient. So actually, we can have this BGL is a quotient of VGL intersect with sphere. This is a submanifold, which is a space of prime choice ripple orbit in the homology class, which is a conjugacy class of G. And we can compute its Collins-Cinder indices. The Collins-Cinder indices so this is always coming in families, but after perturbation, you have a unique one with the smallest period, and the unique one, it also has a minimum Collins-Cinder index. The Collins-Cinder index, rational Collins-Cinder index is this guy. And if you consider C2 coefficient, it's n+1. So we have everything in place. We can talk about how to get topological information about filling from the Symplectic homology. So let's assume that this W is the exact filling of the sphere. The first term class of the filling may not vanish. So we do not have a well-defined grading on your Symplectic cohomology. But the boundary grading, which is because the boundary has first term class 0 rationally, you have the Collins-Cinder index computed before, you have this number. So this will give us a filtration on the complex. And this filtration, well, this will give us a filtration if the singularity is terminal. This is something you can prove by next stretching. And also, you can compare this hypothetical filling W with the given filling CN quotient by G, and conclude that there's actually, compare the induced spectral sequence on both sides, and you can conclude that the spectral sequence, you get a spectral sequence from the positive symplectic homology of CN quotient by G to the symplectic homology of positive symplectic homology of W. Okay, and because of the Z2 grading, these things are all generated by the previous shortest ripple orbit. The Z2 grading all have the same parity. So this spectral sequence collapses. And this will conclude that the positive symplectic homology of the natural filling is the same thing as the positive symplectic homology of the hypothetical filling. Okay? And another thing which is very important is we talk about this SH plus to the cohomology of the filling. This is roughly corresponding to a holomorphic curve passing through a point constraint. And this curve will survive in the hypothetical filling too, if it's terminal. That means when it's terminal, the symplectic homology of W also vanishes. And next thing is the secondary coproduct is compatible with the filtration. Okay. Okay. So these are the kind of things you can get from the Floer-Series holomorphic curve consideration, and they give you very strong topological constraints. So first of all, the hypothetical filling, the rank of the cohomology must be equal to the conjugacy class and supported in even degrees. This is because the fourth bullet, that symplectic homology of W will be killed because the unit is killed. So the cohomology will be the same thing as the positive symplectic cohomology. And from the second bullet, it's the same thing as this one. And we know this one is the size is a conjugacy class. Okay. And second is the coproduct on the associated graded is the same as Chen-Ran coproduct. This is because the fifth part. But since we are working on a spectral sequence, what we can only recover is essentially the leading term. So this is just the leading term. It's the same as the Chen-Ran coproduct. And another thing is because our manifold, this thing sphere quotient by G is a rational homology sphere. It's essentially on homology level, rationally it's a sphere. So coproduct and product are pretty much the same thing. So we can actually also get the information that the coproduct length has this bound. And in particular, it's always smaller or equal to n-2 when it's terminal. And this is something non-trivial. And finally, all of this kind of is coming from compare your hypothetical filling W to the standard filling CM quotient by G. Okay. And the last part is, again, that's something you can prove by Floer-Series, but not by comparing, that this W is simply connected. It's actually fairly easy to see, like, get a feeling why this could be true. It's because of course, we know the boundary. This sphere is not simply connected, but this SH plus is generated by this non-contractible orbit. But this thing has to go into the filling to carry something, so it will bound holomorphic disk. So it's contractible there, and then you have to show that there's nothing else. Okay, so these are all the topological information you can get through the Floer series, this secondary coproduct, and the Floer series of orbifold. Now that this is the end of the symplectic story, let's go to the fun part, which is the topological part, and prove the theorem. So let's assume that, let's go back to the RP2n-1 case. Let's assume that this W is a hypothetical exact filling of the real projective space when n is 2k bigger or equal to 4. Okay, so what we know about the filling from the previous discussion. So first of all, the rational cohomology is supported in degree 0 and n. And second is we have this filling, we can glue it with a cap, which is a total space of degree 2 bounded over Cpn-1. And we know this Euler characteristic is n plus 2. The signature is 2, because we know this kind of the signature of W is 1. Okay, and then we can also get an orbifold, which is using the natural orbifold filling, again glue with this cap. And we can consider the orbifold Euler characteristic. This is n plus 1/2. So 1/2 is because the singularity counted as 1/2. The signature now is 1. This is not on Chen-Ran cohomology, just the regular cohomology. Okay, so since I mentioned the signature, you can guess the thing I want to use is Hertzsprung signature theorem. So here is the Hertzsprung signature theorem, which says the signature is the integration of the L genus. Okay, so here M is n divided by 2. So a priori, the L genus is just some combination of Pontryagin classes. But since our case is almost complex manifold, Pontryagin class can be expressed using Chen classes. So actually, you can express it using Chen classes. And these are the expression. So you have the leading term, an times some coefficient times C2n, which is the top Chen class. And you have a middle Chen class square and some other combination of Chen classes. And the coefficient can be written out explicitly. These are the coefficient. And the Bn is a Bernoulli number. So my convention is it's all positive, and you throw out these 0 Bernoulli numbers. So the first one starts with 1/6. Okay. So I want to use this formula. So in the formula, we basically have to integrate these things on these two manifold and orbifold. I just want to mention that the signature theorem also holds for orbifold, but there will be contribution from singularity. But in the case of the Z2 quotient singularity, there's no contribution from the singularity. So there has been a lot of work on orbifolds. They're trying to generalize stuff from manifold to orbifold in the 50s to 70s by a school of Japanese mathematicians, starting with Sataki. He introduced the orbifold as V manifold. Okay. So anyway, the signature theorem holds for orbifold. And we want to kind of compare them. So in these two manifolds, in these two things, so the integration of the top Chen class is a characteristic class. And the combination of the other Chen classes, since we are in this form, it's the other Chen classes are all essentially contributed by the O2 part. There's no difference between this manifold and orbifold. And another difference between this integration is the integration of middle Chen class. So they basically have two parts. One part is from, because it's separated by a sphere essentially, the two parts. So one part is from the cap, which have the same middle Chen class square. Another part is from the filling part, which the orbifold one doesn't have a middle homology class, but the other guy has. So the difference is just the integration of the top Chen class and the middle Chen class square. So this explains that first we have this difference, and others, except for the C1 square, they make no difference on x and x prime. So what we get is, using the relations that the difference of signature is 1, we get this relation. Okay. And this L is middle Chen class. Oh, sorry, 4L is middle Chen class. You can prove that it's easier to prove L is divided by 2, but you have to make some effort to prove that L is divided by 4. But later I realized you don't need to using this. You can 2L is also, it's easier to get a contradiction. But anyway, this is a relation between this Bernoulli number and the Middleton class, which we do not know. Okay. So we want to derive a contradiction, and you can guess we're just trying to show that this L cannot be an integer, right? Okay. So that means we need to understand the Bernoulli numbers. Okay. So what is Bernoulli numbers? So first of all, there's a very classical theorem called the Clausen-Stout theorem, which says this Bernoulli number is the sum p prime and p divided n minus 1 modulo 1. This is a very classical result on Bernoulli numbers. Basically, it tells you kind of the numerator. What is the numerator? Denominator of this Bernoulli number. So you can write your Bernoulli number in the reduced fraction form like this. And the denominator is like the product of 2 times product of all the primes, such that p minus 1 will divide 2n. Sorry, this should be 2n. Anyway, okay. So the problem is the numerator, and we are only interested in the like power of 2. So let me show you some numerator. So these are the numerators of Bernoulli numbers, n16, n34, and a64. I don't know the number n128, but I'm sure it cannot fit in this slide. Okay, so is there any pattern? Is there some pattern to it? And the pattern, it's an obvious pattern, is that they all end in 17. Right. So the actual pattern is the following lemma, that when n is greater than 8 and its power 2, the numerator modulus 64 is 1. Okay. The denominator is easy because it's in this form. This modulus some power of 2 is easy. Okay. So actually the gesture is this numerators of Bernoulli number modular sum of power 2 at the sequence of power 2 will stabilize. At some point, it will become a constant. But you have to figure out when to stabilize and it is stabilized to what. Okay. So I'm considering this because I want to derive a contradiction from this formula. And this, you can compute it like for small n, compute directly that L is not integer. But a random n is hard. So I want to test the equation by modular numbers. And the simplest number is 2. So let's try 2. Okay. So because of this lemma, okay, so the proof is some elementary, but I didn't know how to prove it, so I Google around these things and find a nice interpolation of the Clausen-Stout theorem. So when n is bigger than 8, that is, you can apply this lemma. You can argue directly L is not an integer by looking at the relation modular 64. Okay, you will get a contradiction. And when n is 8, L is not, so this lemma doesn't hold. So that's before this relation stabilizes. The numerator modular 64 is not 1 yet. But because it's a small number, you can look at the list of Bernoulli numbers and plug in to check it and realize that this L is not integer. Okay. And the most difficult part is n is 4. This L is integer. Okay. So this Hertzsprung signature theorem doesn't give us a contradiction directly. So what do we do? Okay. So first of all, from the previous consideration, we consider from the computation of x, we can actually the missing piece is the Middleton class, which in this case essentially is the middle punctuation class. And we can compute that the integration of middle punctuation class square is 34. This integration is only on the filling, but since my boundary is a homological sphere, so it's like it's well defined. Okay. And then I want to jump out of simplex manifold or almost complex manifold. Let's consider this manifold, which is you glue this filling to itself using an orientation reserving diffeomorphism, which is just take the conjugation for the first coordinate. This preserves RP2, RP7, and then the reverse orientation, which is crucial. Okay, so the end manifold is not doesn't carry. I don't think it carries a almost complex structure. Okay, So we can from, OK, so first of all, the signature is 2, because I use orientation reversing, so both contribute positively. And also, we know the Pontryagin class is just twice of it. It's symmetric. OK, so from the Hurstrich signature theorem, we can again try to find the contradiction, maybe, for this manifold. And we compute it. We find that the top Pontryagin class is 22. It's an integer. So still no contradiction. But you can actually prove that Y is a spin manifold. This is because this W is simply connected. So you can check your spinness just by testing your second Stafford-Whitney class on spheres embedded to it. And if it's contained in W, we know the first string class is 0, so the Stafford-Whitney is 0. So you basically have to consider the case when it's like distributed on both parts. Anyway, it's a spin manifold. So now we can use a stronger version of this integer constraint, which is a Atiyah-Singer index theorem for the Dirac operator, which says if you have a spin manifold, the integration of A hat genus is the index of the Dirac operator, which is supposed to be an integer. But since we know all the characteristic numbers here, we plug it in, compute it, we get not an integer. OK, so this is a contradiction. So this and the proof of RP7 has no smooth fillings. Okay, and the gesture is that like for this kind of contact manifold, we sort of know a lot about the holomorphic curve in it, and that will give us kind of a lot of constraints on some topological information on the filling, and then you try to use whatever you have hand, try to derive a contradiction. So the simplex part has a kind of uniform treatment, but the topological part, you have to be creative. I don't think there's a kind of like the powerful argument to apply to all cases. But as I want to mention that all of the problem here is I do not know the middle Chern class of my hypothetical filling. If I can compare Chern classes to the orbifold, then I can simplify this proof significantly. So it's an interesting question to ask, how do you understand the characteristic class in Floer theory? And I want to mention that characteristic class is a high dimensional information. It's actually encoded in high dimensional moduli spaces. So maybe it will be related to Mihai's talk yesterday, but I think that's an interesting direction to explore. And finally, I have a slide. Since I said the simplex part is general, but the topological part, you have to use some argument. So actually, you can prove a whole list of sphere quotient singularities, so that the link has no exact manifold filling. So here is a list. So there are a few like rather like simple statements like n is 3, and the main reason is we have a classification of terminal singularities in n equals to 3. Okay, so yeah. And maybe the second one is also kind of neat. N is odd, and the conjugate C class is even. For example, when n is odd, the G is Z2. You already get this is very easy to prove. And you also consider kind of finite subgroup of SU2. And for example, when you consider this E6, E7, E8, you know that it has no exact filling whenever n is greater than 2. Okay, and that's it. Thank you.